stuff.
All right. Do we want to start with the Think-Aloud, or should we do like the summaries first?
I guess we could do the summaries. That's what I have right here.
Yeah, you can go ahead. I have like another presentation, but I can go after you.
Okay, sick. Did you make like a slideshow for the summary?
Yeah.
Okay. Shit, yeah, I haven't been making those anyways.
No, I think I'm going like too far with them. It's just like that's just kind of how like I'd want it. Like just make it easier visually for a video.
No, exactly. That totally makes sense. All right. So as far as the summary goes, let me look at these notes here. Obviously, it's talking about the idea of like infinite, but what I thought was interesting, because in my head, infinite is just sort of like a sideways 8, if that makes sense. That's always how I've seen it. It's just like that. But they were talking about it in more of like a concept instead of a numerical value. And obviously infinity isn't going to be a numerical value because there's literally no definition to it. That's the definition of it. But the fact that they were saying the whole like evens and odds type deal, that for every even number it has to have an odd number, just like that's just how numbers work in general. You can't count to that, you can't count that high. But to say that there's an infinite amount of numbers, like, yeah, that'd be the case. Also, I pick up cardinality. It's the number of elements in a set. So it's more so the size of numbers in a set as opposed to the exact numbers in a set. I thought it's again, that sort of ties back to the whole thing of the idea that it's more so the concept of infinity instead of like a numerical like putting a numerical value on it. And so this was probably like the easier chapter for me to understand, again, because it's more like heady and like thought provoking, I guess. So the whole thing with like the guy, the farmer and his sheep, and putting out the rocks to make sure that all of his sheep came back.
Mm-hmm.
I thought was interesting. But yeah, that was my takeaway, I guess.
That was I didn't put anything on like the farmer and the sheep and the stones thing, but that was like an interesting way of like how that German guy, he kind of, that's how we're gonna count infinity, like not by our like 1 2 3, like it's a different, like a simpler way of counting, which I thought was interesting.
Yeah, exactly. It's a cool concept. It's interesting. Yeah.
All right, I will share my screen. All right, can you see me or
I can see.
presentation?
Awesome. I can see your presentation. Yeah.
Awesome, cool. So yeah, basically like it goes on forever. It's, like you said, it's like that figure 8. And so for every huge number produced, there's always a bigger one, which kind of goes into later in the chapter. But there's like even bigger infinities than like other infinities, like it's that big. And mathematicians, like they take like great care in treating infinity like an ordinary number, because it's not. So they like try to make sure like it is not normal. So you have to treat it very special. And like you kind of mentioned, like counting infinity is really interesting. Like that Cantor guy, he came up with this entirely new concept, which basically changed our understanding, as well as the whole concepts of like modern math with it. So yeah, his basically it was kind of like that sheep and stones thing, that whole notion of counting that's simpler than the one we use. And the theory used like sets like n, which represent like all positive whole numbers. And like all these sets lead to subsets, and even n is a subset of q, and like O and E, which represent like odd and even numbers, they are subsets of n. And then like this leads to the question, like, are there the same amount of odd numbers and even numbers? And it kind of goes into that a little bit, and it basically concludes yes, because not because we count and compare all the numbers in the sets. Like, okay, so 1, 3, 5, 7 is equal to 2, 4, 6, 8. But like, probably because of something like half of all whole numbers are odd and half are even. So when you're taking like this infinity of whole numbers, whole numbers, like half are going to be odd and half are going to be even. And Cantor would agree with this, but for a different reason, because to him, he'd say that every time that we have an odd number, there's always going to be an even mate next to it. And this works for comparing sets like even and set n, because like 1, 2, 3, 4, you're going to multiply that by 2 and you're going to get even numbers. So that was also something that I found interesting. And then, yeah, you kind of mentioned cardinality, being that it's the size of the set, number of elements in a set. And it gives like a pretty easy example, like the cardinality of set like A, B, C, D, E is 5, and would be written as like just this, A, B, C, D, E equals 5. And he used this really weird symbol that I drew really bad. It almost looks like a swastika, but it's read as like Aleph naught, to represent the cardinality of n, because that's infinite. So he kind of used a placeholder to represent the cardinality. And it kind of talks about how any set that can be put in like a total correspondence with n is called countably infinite, meaning that we can write the elements of the set in a list, like we do for even numbers 2, 4, 6, 8, and then just do that ... and you know that all the other numbers in that set are going to like be based on that. I think I should put 10 as well.
That they like follow suit and then just go continue.
It basically like follows this like pattern. And then it goes into like our fractions, countably infinite, and this part was a little confusing, but some of the stuff that I got out of it is that n is a subset of set q, which I also mentioned, and set q is basically like all the numbers, including negative numbers, 0, and positive whole numbers, which would be set n. And because of that, it has 2 times as many numbers as n, because for every positive whole number, you're going to get negative whole numbers. And in the case of set q, like it asks, like, is there a list? So every fraction in set q is somewhere on it. And it uses this like graph where it does like all these different dots. And that's basically a way to find, like, put it on a one-dimensional plane and making it technically countably infinite. I didn't really understand it, but that's what I got out of it. It's a tough thing to kind of understand this stuff. And then it goes into like listing real numbers. Irrational numbers aren't fractions or whole numbers, and they fill in the gaps to give us the number line r, which this is number line r. And with the gaps kind of filled in, set r is referred to as the continuum. So to make, spelled his name wrong, to make a list of the real numbers, Cantor showed that it's incredibly difficult to list the real numbers that reside between 0 and 1 because there's just so many. And he had like a formula to represent it, but they kind of use that to kind of come to the conclusion that it's so difficult that it's impossible to make a list for set R as a whole, let alone for 0 and 1, which kind of makes it a larger infinite set with a higher level of infinity than the infinity in set Q, because there's like an infinite amount more numbers than there are than -1, -2, -3, because for each number there's an infinite amount more. So it's like infinity in infinity. It's like infinity inception in set Q. So it kind of ends the chapter on like infinite just got bigger, because there's like a whole nother level of infinity.
And it keeps expanding. It's
Which is
yeah.
crazy. And yeah, that's all I had.
It's like actually infinite. Yeah, that's kind of cool.
Mm-hmm.
Interesting. Good stuff. Yeah.
Yeah.
So do you want to keep recording with the Think-Aloud, or is that how does the
Yeah, I'm still recording. Yeah, let's do the Think-Aloud. Did you have any parts of the chapter that you think would be like good, or I don't have anything either.
I mean, not. I think like the easiest one that that would be easy to like talk about, I guess, is sort of either what you were just talking about, the fact that like you imagine infinite and then you think about like, okay, well, there's a whole other infinite sets of numbers within that, and it just keeps expanding.
Yeah.
That or that would be cool. And then again, I mean, you talk about like the concept of infinity, but yeah, I think the only one that I had a problem with was the fractions. Can fractions be infinite? I kind of saw that. I was like, oh, that's dense.
Yeah. We that could be cool, just to we can kind of bounce our ideas off that and kind of read that again. But yeah, which one sounds better for you? The like listing real numbers or like the fractions? Just kind of.
I would
I'm
say,
cool with whatever.
okay, cool. I'd probably say maybe the real numbers thing, just because it makes I have a better grasp on it.
Be
Yeah,
easier.
yeah.
All right. Yeah, I will share my screen again. And let me know if you can see this.
Oh yeah, I can see it. You're good.
You can see the chapter. All right, cool.
Mm-hmm.
Yeah. Okay. So, what parts? I don't think we have to read all of it, but
Okay, let's see here.
actually, it's not that long. Are you
No, it's a
fine
pretty.
reading all of it?
Yeah, no, totally. So how does this work? I basically just run through it and then explain it as it's going on.
Yeah, we can switch off with each paragraph, but yeah,
Okay.
like we can just, as we're reading, we like, oh, so yeah, this means this, that means that, stuff like that.
Okay, cool. Let's see here. Listing the real numbers. While the set of fractions accounts for many elements on the real number line, there are also real numbers like square root 2, e, and a, which are not fractions. These are the irrational numbers. They fill in the gaps to give us the real number line r. Yeah, so I guess that's the whole thing. I mean, it's exactly what it says. There's basically numbers within each number, and sort of like an infinite amount of those, and it kind of just that was my grasp on it, I guess.
Yeah, no, yeah, that totally makes sense. And kind of just going back to like 0 and 1, because that's like my easiest way of going back to it. Like you go to like 2/3, and that's like an infinite number, and that's put like in the like 2/3 spot on here. But
Yeah.
yeah. And so with the gaps filled in, the set R is referred to as the continuum. So how could we make a list of the real numbers? In a move of sheer brilliance, Cantor showed that even an attempt to put the real numbers between 0 and 1 into a list is doomed to failure. This will undoubtedly come as a shock to people who are addicted to list making, and they may indeed wonder how a set of numbers cannot be written down after another. Yeah, I don't think there's much in this paragraph other than like, oh, it kind of implies that there's so much between, say, 0 and 1 that like it's almost impossible to make a list of how many numbers are on there.
Yeah. No, it totally makes it. That's like I think that was again for this like entire chapter too. That was my biggest takeaway, was the fact that you want to understand what infinity is, but the whole entire point and like point of infinity is that it's not. There's no value to it. It's because it's just forever ongoing.
Yeah.
Suppose you did not believe Cantor, you know that each number between 0 and 1 can be expressed as an extending decimal. For example, 1/2 equals 0.5 and just ongoing. And 1 over, I'm going to say n, but
I think it's pi, actually.
Oh, is that pi? Okay. Yeah, and 1 over pi equals, oh yeah, you had 0.3183 again ongoing.
Yeah.
And yeah. And you would have to say, Cantor, here is my list of all the real numbers between 0 and 1, which we'll call R1, R2, R3 throughout. If you could not produce one, then Cantor would be correct. Imagine Cantor looks at your list and he marks in bold the numbers on the diagonal. Oh shit, that's interesting. Yeah.
Yeah, because like for each of these R's, there's an infinite amount of decimals, that type of
Yeah.
stuff. So Cantor would have said, okay, but where is your number x equals 1, x1, x2, x3 repeating? Where x1 differs from a1, x2 differs from b2, x3 differs from c3, working our way down the diagonal. His x differs from every number on your list in one decimal place, and so it cannot be there. Cantor is right. In fact, no list is possible for the set of real numbers R, and so it is a larger infinite set, one with a higher order of infinity than the infinity of the set of fractions Q. Big just got bigger.
Huh. That's
Yeah,
makes
it's crazy.
Yeah. It's a pretty intense concept. I feel like it's just like no matter how many times you look into something, it's just like, oh nope, there's no end.
Yeah.
Um, but the way that he's explaining it too, which is interesting, is that like I've always thought of infinity as like the only way to visualize it is sort of like space, where you just keep going out and out and out, and there's no end to it. But the way that he's talking about it is like magnifying and like going in and it like it just continues to go further in. It's always going to be infinite, but more in like a magnified sense, not a pulling back sense.
Yeah.
I mean, I guess it works
Yeah.
either way. Yes, yeah.
Definitely. Yeah, but other than that, unless you have anything else to kind of add, I think that's all we got. Yeah.
Cool. I think we're